A silicon wafer comes out of SMIC's advanced fabrication facility and, under close physical analysis, it carries a timestamp that no marking on its surface records. The timestamp is in the geometry itself. Teardown analysis of chips believed to originate from SMIC's most advanced production line, work that drew broad attention when it examined the processor inside the Huawei Mate 60 Pro in 2023, identified transistor feature pitches consistent with what the industry classifies as 7 nanometer class density, and on certain layers approaching what analysts describe as 5 nanometer class pitch. That surface, examined at the scale of individual transistor gates, looks like the output of equipment SMIC does not possess. The dissection of this one wafer will show why, and the deepest layer is not a materials finding, it is a counting finding. The cuts run from the finished surface inward, surface geometry first, then the patterning sequence that built it, then the self-alignment mechanism that holds 4 sequential exposures coherent, then the process step arithmetic that each added pass generates, then the yield structure that step count loads onto every wafer, and finally the deepest layer, where the shape of the equipment restriction becomes legible in the silicon itself. The surface of this wafer is where the dissection begins because the surface is where the product lives. Transistor gates are drawn at the surface. The density of those gates determines the computational work a given area of silicon can perform, and density is set by the minimum pitch, the center-to-center distance between adjacent features, that the manufacturing process can resolve. The teardown analysis measures that pitch directly on finished silicon. It does not rely on any claim SMIC has made about its process node, because SMIC has not published process node specifications in the conventional way that foundries typically do. What the analysis finds is a physical dimension on a physical object, feature pitches that, on certain critical layers, fall in the range the industry associates with advanced density nodes. The label attached to that range, whether it is called 7 nanometer class or approaches 5 nanometer class, is a descriptor for a pitch measurement, not a claim to any official process designation. The surface, examined this way, states a fact about what the wafer achieves. Everything below the surface is the explanation of how it achieves that without the tool the surface implies. The surface geometry of this wafer, then, is a specification written in silicon, and the specification exceeds what deep ultraviolet lithography can write in a single pass. That gap between what the surface shows and what a single exposure of the available equipment could produce is the seam where the next layer of the dissection begins. Deep ultraviolet lithography operates at a wavelength of 193 nanometers. The resolution limit of an optical system is fundamentally tied to its wavelength. Finer wavelengths can resolve finer features. At 193 nanometers, a single scanner exposure cannot directly print features at the pitches visible on this wafer's surface. The industry has known this boundary for many years, and it developed a class of techniques to work around it without shortening the wavelength. The generic term is multi-patterning. The principle is that if a target pattern is too fine to print in one pass, it can be decomposed into 2 or more sub-patterns, each of which is coarser than the target and therefore within the scanner's resolution capability, and those sub-patterns can be printed sequentially on the same layer. When the sub-patterns are combined in the physical layer, through deposition and etch steps between exposures, the result is a pattern finer than any single pass produced. Self-aligned double patterning doubles the feature density relative to a single exposure. Self-aligned quadruple patterning doubles it again, reaching 4 times the density of a single pass. These are not theoretical constructs. They are established production techniques used across the industry on layers where EUV was not yet available or was not cost-effective. What the teardown analysis suggests about this wafer is that its most critical layers, the ones carrying the densest features, were processed through at least quadruple patterning. The number of passes is not printed on the surface. It has to be inferred from the finished geometry and the known resolution limits of the equipment believed to be in use. The inference is that the layer was exposed to deep ultraviolet light at least 4 times in sequence with etch and deposition steps between each exposure to reach the pitch the surface displays. Whether the most aggressive layers push further toward what process literature describes as octuple patterning is a claim that available public reporting has not independently confirmed for SMIC's production line, and this dissection treats that possibility as under investigation rather than established fact. The reason 4 exposures can produce a result that 1 cannot is the self-alignment mechanism, and this is the layer of the dissection that carries the most structural weight. In a self-aligned quadruple patterning sequence, the second and subsequent patterns are not registered to the wafer's coordinate grid directly by the scanner's stage. They are registered to the edges of features that the first pass already created. The process works as follows. The first exposure prints a set of features, called mandrels, that are coarser than the final target pitch but within the scanner's capability. A spacer material is then deposited conformally over those mandrel features, covering their tops and sides with a film of controlled, uniform thickness. The spacer film is then etched back in a way that removes it from horizontal surfaces while leaving it standing on the vertical sidewalls of the mandrels. Those sidewall spacers, 2 flanking each mandrel, become the etch mask for the next stage of pattern definition. The mandrels themselves are then selectively removed, leaving only the spacers. Because each mandrel produced 2 spacers, and the mandrels are then gone, the spacer array has twice the feature count of the original mandrel array at roughly half the pitch. Repeating the sequence, depositing spacers over the first generation spacers, and using those second generation spacers as the next etch mask, doubles the density again, reaching quadruple the original mandrel density. The mechanism that makes this work is the word self-aligned in the technique's name. The spacers are grown from the existing features rather than written by a new optical exposure, so their position is determined by where the previous features already sit, not by the scanner's ability to place a new pattern at a precise coordinate. The precision requirement has been transferred from the scanner's overlay system, its ability to register a new exposure to an existing pattern, to the deposition chamber's thickness control, which can be managed to near atomic layer precision. Consider a craftsman who cannot cut a plank to a precise width directly because the measuring instrument lacks the resolution. So instead, the craftsman lays a shim of known thickness against the first cut and scribes the second line from the shim's edge rather than from the ruler's markings. The shim's physical dimension, not the ruler's resolution, determines the final spacing. Self-aligned quadruple patterning does the same thing at the scale of nanometers, using deposited film thickness as the precision reference. A single spacer at the pitches being discussed is roughly as wide as a strand of deoxyribonucleic acid is long, a physical scale worth holding in mind as the mechanism is described. This mechanism is the engineering response to a specific problem. If each successive exposure in a 4-pass sequence had to be registered optically to the previous one, the cumulative overlay error, the sum of small positioning inaccuracies from each alignment step, would by the 4th pass exceed the feature size being targeted. At 5 nanometer class pitches, the permitted misregistration for the final pass is smaller than the features that the first pass printed. An optical registration strategy cannot meet that tolerance across 4 passes. The self-alignment technique sidesteps the problem by not requiring optical registration for the critical pitch-defining steps. That is not a minor optimization. It is the reason the technique works at all. The teardown reports that characterize the finished feature pitch on this wafer identify the result. They do not always identify that the result required SMIC to solve an alignment problem of this specific character, one that extreme ultraviolet lithography sidesteps entirely by printing the final pitch in a single pass that requires no self-alignment architecture at all. The wafer on the table carries this mechanism in its cross-sectional record. What appears at the surface as a uniform array of fine, evenly spaced features is, in the layers beneath the surface, a stratigraphic sequence of spacer generations grown from a coarser original pattern. The tidiness of the surface obscures the construction history beneath it, and that construction history is what this layer of the dissection is exposing. Each additional patterning pass in a multi-patterning sequence does not add one step to the process. It adds a cluster of steps. The spacer material must be deposited. The deposited film must be annealed or cured to stabilize its properties. The etchback that defines the spacer edge is a separate operation. The selective removal of the mandrel material, which must not disturb the spacers that will serve as the next etch mask, is another. In many implementations, an inspection step follows before the process continues because a geometry error at this stage propagates through all subsequent steps and cannot be corrected after the mandrel is removed. Published process literature and analyst descriptions of multi-patterning stacks suggest that moving from a single deep ultraviolet exposure to full quadruple patterning on one layer can add on the order of a dozen discrete process steps for that layer alone. The specific step count for SMIC's advanced node process is not publicly confirmed, so this is presented as an approximate range from published descriptions of similar processes, not as a verified figure for this specific fab. The consequence of that step count extends beyond the wafer itself. Each step occupies time on processing equipment. The equipment that performs spacer deposition, etch-back, and mandrel removal is not the lithography scanner. It is a separate set of tools that must be available, scheduled, and functioning for every wafer that passes through the advanced node process. A wafer produced on a single-pass extreme ultraviolet line occupies scanner time and the subsequent etch step. A wafer produced on a quadruple patterning deep ultraviolet line occupies scanner time 4 times, plus the deposition and etch equipment for each spacer generation. The throughput of the advanced node process and the number of wafers the fab can complete per unit time is lower for the same reason that the step count is higher. The wafer on the table is not simply a more complex object than an extreme ultraviolet printed pier. It is a slower object in the sense that its production consumes more of the fab's capacity. That time cost is embedded in the finished wafer as surely as the feature geometry is, and it does not disappear as the process matures. Yield, the fraction of dies on a finished wafer that meets specification, is the point where process complexity converts into economics. Every step in a semiconductor process introduces a probability of producing a defect. A particle landing on the wafer, a slight non-uniformity in etch depth, a positioning error in pattern placement, any of these can render a die unusable. The relationship between step count and yield is multiplicative in character. If each step has a small per-step probability of introducing a defect, the combined probability of a die surviving all steps without defect falls as steps are added. More steps mean more opportunities for defects, and the yield of the finished wafer reflects the accumulated probability of all those opportunities. Analyst reporting on SMIC's advanced node yields has consistently characterized them as below the mature yields observed at TSMC and Samsung on comparable density nodes. These characterizations are indirect. They are inferred from shipping volumes, customer commentary, and analyst channel checks rather than from any primary measurement at the die level. And they should be read as qualitative estimates rather than verified figures. The uncertainty is real, but the directional observation is consistent across sources, and the dissection offers a structural explanation for why. Part of the yield gap between SMIC's multi-patterned wafers and extreme ultraviolet printed piers is not a function of SMIC's process maturity. It is inherent to the architecture. Each added patterning pass adds defect opportunities that a single-pass extreme ultraviolet exposure does not create. The yield improvement that comes from running a process for longer and accumulating learning will reduce the variable component of the yield gap. It will not eliminate the fixed component, which is the structural contribution of the additional passes and their associated steps. Reports that describe SMIC's yields as early or ramping, implying that time alone will close the gap, do not always make this distinction. The wafer on the table exits the fab at a yield that combines both a learning curve component and an architectural component, and from the outside, those two contributions are not separable. Reading yield figures for this wafer requires holding both in mind simultaneously. The deepest layer of this dissection is the one that names what the multi-patterning architecture is substituting for. Extreme ultraviolet lithography operates at a wavelength of 13.5 nanometers, roughly 1/14 the wavelength of the deep ultraviolet scanners SMIC operates. At that shorter wavelength, the resolution limit of the optical system is sufficiently fine that the critical layers now processed by SMIC through 4 sequential patterning passes can be printed in a single exposure. TSMC began volume production using extreme ultraviolet lithography on its most advanced nodes in approximately 2019. Samsung followed on a comparable timeline. The transition to extreme ultraviolet on critical layers was not driven by preference or novelty. It was driven by the fact that extreme ultraviolet reduces process complexity, cycle time, and defect density simultaneously on the layers where multi-patterning had become the bottleneck. ASML, the Dutch company that manufactures extreme ultraviolet lithography systems, is the only supplier of those systems in the world. Export controls administered by the Dutch government in coordination with policy from the United States have blocked ASML from delivering extreme ultraviolet systems to customers in China. SMIC has not received extreme ultraviolet equipment. No credible reporting suggests a path to acquisition under current policy conditions. These are documented policy and commercial facts, not analyst estimates or inferences from teardown data. The surface geometry of this wafer did not require 4 patterning passes because of any property of silicon, any limitation of circuit design, or any choice SMIC made from a menu of equivalent options. It required 4 passes because the tool that would have produced the same surface geometry in 1 pass is not in the fab, and the reason it is not in the fab is a policy decision made and enforced outside China. The 4 passes are not an alternative approach to the same destination. They are an engineered substitution for an absent tool, and the substitution carries cost in step count, in cycle time, in yield that the original tool would not have imposed. Every spacer deposition step, every etch back, every mandrel removal, every additional inspection pass is a material consequence of that policy decision. The wafer is, at this depth of analysis, a 3-dimensional record of the restriction. The restriction did not stop the wafer from existing. It shaped what the wafer had to become in order to exist. The dissection cannot settle 3 things, and they should be named plainly. First, the gap between SMIC's process characterization and independent physical verification cannot be resolved from available teardown data alone. Node labels in the semiconductor industry have not been standardized for a number of years. A pitch measurement on a specific layer of a specific chip is a real finding. Whether that measurement constitutes the full definition of what the industry intends by a given node designation is a question the teardown analysis cannot answer on its own, and SMIC's own characterizations of its process node have not been offered in the standard form that would allow direct comparison. Second, yield figures for SMIC's advanced node are not available from any primary source. Every yield characterization in this dissection is a qualitative inference from indirect evidence, shipping volumes, analyst channel checks, customer commentary, and the uncertainty in those inferences is large enough to affect any quantitative conclusion drawn from them. Third, whether multi-patterning can be extended beyond quadruple patterning to octuple patterning at production relevant yield on a deep ultraviolet line is genuinely contested in process engineering. The cumulative overlay error from additional spacer generations, the defect density from the additional steps, and the thermal budget constraints of sequential processing all impose practical floors on the technique. Whether SMIC has reached those floors or retains practical headroom above them is not determinable from available public information. The mechanism described in this dissection is established with confidence. The yield and step count consequences follow from the mechanism with reasonable certainty. The specific magnitudes, the exact yield figures, the exact step count, the precise limit of the technique, are estimates, and the dissection's reading does not require the precise numbers to stand. The mechanism is sufficient. Put the wafer back on the table and describe what the cuts have found. A surface that achieves transistor density consistent with advanced node production. A patterning sequence that required at least 4 exposures on critical layers and their associated deposition and etch steps to reach that surface. A self-alignment mechanism that exists specifically because 4 optical exposures would accumulate too much alignment error without it, and that borrows precision from deposition thickness control to compensate for the scanner's overlay limits. A yield structure that carries a fixed architectural cost from the added passes, in addition to the variable cost of process learning. And at the deepest layer, an absence, the extreme ultraviolet scanner that was never delivered, whose precise shape is legible in the geometry of what replaced it. The wafer is a capable object. It produces transistors at a density that would not have seemed achievable on deep ultraviolet equipment a decade ago, and it does so through a multi-patterning architecture that represents a genuine engineering accomplishment under constraint. It also carries, in its layer structure, a permanent record of the constraint that shaped it, and that record is not erased by process learning, by further yield improvement, or by any refinement of the technique that does not remove the additional passes themselves, The restriction meant to stop this wafer from existing is the reason every critical layer inside it was printed 4 times. That is not a reading imposed from outside the silicon, it is what the construction of the silicon shows. What the export control intended to prevent, it instead preserved, in the layer structure of the very object it was meant to stop. The next object on the table is a memory chip that bonds 2 wafers face to face, and the question is what that vertical stack accomplishes that a single taller wafer cannot. If that is the dissection you want to see, leave it in the comments. And if this approach, taking one object apart cut by cut until the deepest constraint is visible in the structure itself, is how you want to understand what is happening in semiconductor manufacturing, subscribe and turn on notifications because there are more objects on the table.